All right, and hello, AP Stats students. Today we're going to start section 12.1. We're going to start talking about inference for linear regression. So 12.1 will be linear regression, 12.2 is transforming, and that's going to be the end of the year after we're done with this chapter. So let's start by talking about the helicopter experiment that you guys explored yesterday. The scatter plot that you made should have looked something like this. Okay. And then the least squares regression line should have had a slope of about 0.287 and a y-intercept of negative 0.123. Okay. And then interpret the slope. So to interpret the slope, this number let's say 0.29, what does that mean? So the slope means for every one increase in your explanatory variable, that's the predicted increase in y. So this variable down here was drop height. This variable right here was the time it took to fall. So what that means is if you increase drop height by 1 foot, the expected increase in time it takes to fall is 0.287. That's what the slope means. So what is your best guess for the increase in descent time for each additional foot of drop height? Well, that's basically asking you, that's the interpretation of slope right there. So our best guess would be this number right here. Now, do we think this is exactly true for every possible plane? Well, no, probably not, but this is a good ballpark. It's going to be somewhere close to this, we think. We studied quite a few of the helicopters, so we think that number will be about right. Does it seem plausible that there is no linear relationship and that this observed slope just happened by chance due to random assignment? Like, for example, this plane right here, let's say, plane number, 18, or helicopter number 18. Was it possible that this helicopter was always going to take this much time no matter what height we dropped it from? And that it was just because of random assignment that we saw this increase? And I hope your answer there was, yeah, definitely not. Does it seem plausible that there's no linear relationship between these two variables? Yeah, absolutely not. There's no way we could have just randomly assigned these 50 helicopters in a way that gave us this, a positive slope here. So we're going to look at how to actually answer questions like that using our, more complicated statistics. So here we go. Let's talk a little bit about linear regression. Back in chapter 3, if you remember, we looked at data for eruptions of the Old Faithful geyser, and we looked at this scatter plot, if you remember, of the interval of time until the next eruption for all 222 recorded eruptions in a single month. And then we made the least squares line for this population that had a slope of 10.36 and y-intercept of 33.97. This is called the population regression line, or we can call it the true regression line because it's based on the entire population. It uses every observation from the month. Now, let's say that we took a simple random sample of 20 of these eruptions, and then for those 20, we calculate the least squares regression line for that sample data. So how is that sample regression line going to be related to this true regression line? Let's take a look at a few examples here. So each one of these, if you can see here, the blue dots, or the kind of bluish-green dots, are the sample of size 20, which creates this line, which has this equation right here. If I take a different SRS, I get these 20 bluish dots, and I get a different line, which has an equation right here. And then sample 3, there are 20 kind of bluish-green dots here. Those would give this line, which has this equation right here. Now let's look at those equations, and really let's focus on the slope. Take a look at these slopes. I got 10.2, I got 7.7, I got 9.5. If you think back to the population had a slope of 10.36. So one of these was pretty close, but this one was a little lower, this one was quite a bit lower. So as you can see, the slopes vary quite a bit compared to the true regression line slopes of 10.36. it would be possible to get a bigger slope as well, or even a lot bigger, depending on what 20 eruptions are sampled. Now the pattern is described of what these slopes will be is described by a sampling distribution. Let's say that I took a bunch of samples of size 20, not just 3, but I did like 1,000 or 1 billion more, okay? And then I just kept track of all the slopes. So here are all the slopes if I did that a whole bunch of times. This is called a sampling distribution, or the approximate sampling distribution for the slope of the true regression line. All right, because this is 1,000 SRSs of size 20 from this data. Let's talk about what this sampling distribution looks like. It has a symmetric shape. It appears to be single-peaked. It appears to be, unimodal. And if you do take this and make a normal probability plot, it does look like that this is an approximately normal sampling distribution. The center of this sampling distribution, right at that red line, you can see there is a little more than 10, which is right around that true regression line slope. So these 1,000 happen to have an average of 10.32, while the true slope of the regression line is 10.36. The spread of this can be measured by finding the standard deviation is 1.31, and later we will see that the standard deviation of the sampling distribution is actually 1.30 if you did every possible one instead of just these 1,000. All right, so the slope, we'll call it B, and the intercept, we'll call that A, of the least squares regression line are statistics. That is, we can calculate them. For individual samples, we can get different values. Now, these statistics would take somewhat different values if the data, if we repeated that process over and over again. So to do inference, we think of A and B as estimates of unknown parameters alpha and beta, where alpha and beta are the true, slope and y-intercept of the population regression line. Now, conditions for regression. Suppose we have n observations of an explanatory variable x and a response variable y, and we want to study or predict the behavior of y for given values of x. The conditions are not our normal 3 conditions. We have more than that. We actually have 5 conditions here. There is the linear condition. That means the true relationship for x and y is linear. So for any fixed value of x, there's some response where the average response falls on the regression line. The slope beta and the intercept alpha are usually unknown parameters. There's the independent condition, and this one we're familiar with. It's that individual observations are independent. There's the normal condition, which is the same name, but we test it a different way. The normal condition is that for any fixed value of x, the response variable y varies according to a normal distribution. We'll talk more about that in a second. There's this new condition called the equal variance, and that is the standard deviation of y, call it sigma, is the same for all values of x. The common standard deviation sigma is usually an unknown parameter. And then there's the random condition, this one as we're used to. The data come from a well-designed random sample or randomized experiment. Let's talk a little bit about what each of these actually means. So here is kind of my picture to show the conditions, which is kind of like a 3D picture. So here's my scatter plot. Here's that line. And basically the idea is for each possible value of x, so let's pick one value for x, like x1, do the y values have a mean that's right on this line? That's the idea here for that linear condition. The other idea here is that these normal curves show how y will vary when x is held in a fixed position. So let's say I hold a fixed position, so I just look at dropping helicopters from a single value, 6 feet. They'll be centered. The average time to fall will be centered right on this line, we hope, but how will they be spread above and below that average? The idea here is that they will be spread around that middle according to a normal distribution. So most will be close to the line and then fewer the farther away from that you go. And then also, all of these curves have the same standard deviation no matter which value you pick for x. That's the equal variance, is that there's equal spread for any place on this line, for any fixed value of x. Now the value of sigma determines whether the points fall close to the line or are widely scattered. That's what that is measuring. So let's do these 5 conditions again, and the way you can remember them is this abbreviation LINER, L-I-N-E-R. L stands for linear. So the way you check that is you examine the scatter plot and check the overall pattern is roughly linear. You look for curve patterns in the residual plot and you check to see if the residuals are centered on that residual equals 0 line. The independent condition, you look at how the data were produced. Random sampling and random assignment will help ensure independence of individual observations, and again, if you're sampling without replacement, check that 10% condition. The normal condition, you can make a stem plot, histogram, or normal probability plot of the residuals and check for clear skewness or other major departures from normality. Basically, we can't check it for each individual value of x, so we lump them all together and make a normal probability plot of the residuals. Equal variance. You look at the scatter of the residuals above and below the residual line on the residual plot, and it should be roughly the same for any value of x. And random, see if the data were produced by a random sample or randomized experiment. You'll notice many of these, 3 of these 5, use the residuals or the residual plot, so that's something very important to look at. All right. I'm going to move on to this example instead. So Mrs. Barrett's class did a variation of the helicopter experiment just like we did. They randomly assigned 14 helicopters to 5 different drop heights, those 5 numbers. They released 14 from each for a total of 70, and they got the following results. Here's the scatter plot, and then here would be a residual plot of their data. Here would be a histogram of the residuals, and here would be a normal probability plot there of the residuals. Okay, so let's look at how to check all the conditions. We're going to start with the linear condition. The linear condition we can check just by looking at this graph and saying, hey, it looks pretty linear. Or we can look at this graph right here, the residual plot, and said, hey, it looks like there's a random scatter above and below that line. So those are kind of the 2. Oh, and there's residual plot shows, random scatter above and below, and this looks pretty linear. That's what we look for to test the linear condition. Let's see. Li, independent. The independent condition, we look at how the data were produced. Because the helicopters were released in a random order and no helicopter was used twice, that means they are independent from each other. And the normal condition, I look at the plot, the histogram of the residuals, or the normal probability plot of the residuals. This looks, symmetric, unimodal, roughly normal. This normal probability plot has a linear shape, so that meets our normal condition. Equal variance condition. I look at the spread above and below the line 0 for each value of x. I'm noticing a slight issue. If I look at the spread from here to here, and here to here, and here to here, and here to here, those are all roughly the same, but I'm noticing for this value, I have a little bit larger spread. Okay, so it seems to vary more for helicopters at this 307. So I might have some concerns about equal variance here. And then random, I look at how they were produced, and yes, the helicopters were assigned randomly. So in conclusion here, we have a slight concern about equal variance, but that's just a small concern, so we should be safe performing inference about the regression model in this setting. So that's where we're going to stop today. Please let me know if you have any questions.